Hi. This time we're going to look at the notebook that demonstrates a special type of locality called row versus column majority. Okay, so what we are talking about are two-dimensional arrays and the way that you should traverse them. So in a previous video, we already saw that arrays are better than linked lists in terms of locality. But now we're going to look at a more detailed view for a two-dimensional array. So NumPy array, by default, are organized in a row major order. So what does that mean? So if I define an array in this way, and then I print it in a pretty way, you see that the index of the elements increases with the column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then only increases with a row. So that's called row major. So in other words, if you look at locations aij and aij plus 1, they are placed in consecutive places in memory, while aij and ai plus 1j, the next row, they are 10 memory locations apart. Okay, so in reality, you would think about this as maybe being 1,000 places apart in big arrays. So this implies that if you scan the array row by row, you have more local access and it'll run faster than if you access it column by column. And locality implies speed, so this will run faster. So let's see. Here is a scanning of column by column. So what we're doing here is for I in the range n, I sum all of the elements, all of the rows for column I. And that takes 12.46 microsecond. While if I scan it row by row, I do the same thing, but now I basically take all of the elements of the row, then you see it's about half as much time. Okay? And that is basically because of the memory locality. So here we're going to run a little experiment to see how this actually behaves. So we have some code. You can see the detailed code if you go to the notebook. And this code basically runs, generates an array that is square, so it has the same number of rows and columns. Number of rows and columns is 10 to the e, so we're talking about something going up to 1,000 rows and columns. And you repeat each experiment k times. And then we're going to plot it. And what we see here is the x-axis has the size of the matrix, or the size of one side of the matrix. So 1,000 means 1,000 by 1,000 matrix. And this is the amount of time, the ratio between the amount of time it took to do it column-wise versus row-wise. So you see that as the size of the matrix increases, the ratio between the amount of time also increases. And it's more or less behaves like a square. The other thing that you see here is that it is actually very noisy, because if you take, here we take individual runs really differ a lot between runs, because the state of the cache is varying very rapidly, and if we catch it in an empty space, we basically do things faster than if we catch it in a situation where it's already highly loaded. So what did we learn from that? We learned that traversing a NumPy array column by column takes more time than traversing it row by row. And the effect increases proportionally to the number of elements in the array. and that the effect is highly variable between runs. Okay, so this basically gives you a sense of how access locality, because of row traversal or column traversal, looks. So I'll see you next time.